In this second video, I will talk about the demand for children in the Unified Growth Theory model by Strelick and Weisdorf. The aim of the video here is to first review the assumptions about population dynamics in this model, and then to show you how to derive the demand for children as a function of the price of food in this very model. Let's start with the setup of this model. So here we have an overlapping generation model, meaning that at every period, at any point in time, we have two categories of agents, that we will call the children and the adults, and these two generations keep replacing one another. The children generation, which is born in period T, basically does nothing except consuming 1 unit of food at the expense of their parents, the adults. The adults in T, so those that were born in period T minus 1, supply 1 unit of labor. They can choose how many children to have. In that case, they have to feed them. They can choose as well how much of the consumption good they want to consume in the limit of the budget constraint. And then at the end of the period, they simply die. Then in period T plus 1, the old adults are dead. The children of period T become adults in period T plus 1, and these new adults have in turn some children. In order to keep things simple here, we'll assume that reproduction is asexual, which means that we assume that one single adult gets NT children. So the dynamics of the labor force is quite simple here. Adults are all identical. They all make the same decision about the number of children LT that they want to have, and then LT plus 1, the labor force in period T plus 1, is equal to NT times LT. Here, an important point that should be stressed is that NT is the only choice variable in this situation for the adults. So NT is the only endogenous variable in the model. In terms of preferences, we know that adults like two things. They like manufacturing goods, which we denote as MT, and they like to have children, NT. We'll assume that their preferences are represented by a quasi-linear utility. So the utility of adults in period T, UT, is a function of MT and NT, which is equal to MT plus gamma times log of NT, where gamma is some parameter. In terms of the budget constraint, we need to take into account the price of the different goods. So the standard manufacturing good M has a price of 1 by normalization, while the relative price of food is denoted as P index T. For simplicity, we'll assume that people consume food only when they're young, so they don't consume food as adults. They need 1 unit of food per child. Therefore, for the adults, the cost of raising one child is 1 unit of food, or PT. Then the budget constraint of any adult in this economy is PTNT, the cost of raising children, plus MT, the cost of manufacturing goods, which should be equal to WT, where WT is the income of the adult. So in this video, we won't try to determine the income of the adults here. So we just assume that this is something that is given to us. I now move on to the more technical part of the video, where I compute the demand for children. In our case, the adults make two different choices, the choice of MT and NT. So they maximize utility with respect to these two choices. They are subject to their budget constraint. There are several methods we could use to solve this utility maximization program. The first one would be to use the budget constraint and, for instance, replace empty in the utility. I'm not going to use this type of solution, rather use the Lagrangian as an example. So we'll take into account in the Lagrangian both the objective, mt plus gamma log of nt, and the budget constraint. So we'll add a lambda times wt minus ptnt minus mt, so that's the thing that should remain at least equal to 0 or positive. When we solve using the Lagrangian method, we need to write the two first order conditions with respect to the two choice variables. So first I write the first order condition with respect to mt, so dl over dmt is equal to 0, which is equivalent to 1 minus lambda equals to 0, or lambda, the Lagrange multiplier, is equal to 1. Then the second first order condition with respect to nt, dl over dnt is equal to 0, is equivalent to gamma over nt minus lambda times pt, the price of food, is equal to 0, which in turn is equivalent to gamma over nt equals lambda pt, but we know that lambda is equal to 1, so we obtain gamma over nt is equal to pt. So here, this second first order condition means that the marginal utility of one child, gamma over nt, is equal to the price of raising one more child, which is quite easy to understand. Once we have this equation, it's quite easy to invert and obtain NT, the demand for children by adults. So NT is equal to gamma over PT. Several things should be noted once we have the result. NT is equal to gamma over PT means that, of course, the price of food negatively impacts the number of children that the adults want. On the other hand, you can see in the expression here that NT is not impacted by the income of adults, WT, which we interpret as some kind of strong preference for children. Here the income does not affect N, or we'll say using technical words that there is zero income elasticity in this demand for children, so which means that the adults only take into account the price of food here. Once you take a look at the production part of the model, which I'm not talking about here, you'll see that productivity growth in both sectors will have an impact on fertility, although the impact is indirect here because it goes through price changes. Indeed, if the productivity in the agricultural sector goes up, then the relative price of food compared to manufacturing goods will decrease, which means that fertility will increase. On the other hand, if the productivity in the manufacturing sector increases, then the relative price of food will increase, which means that fertility will decrease. How does this simple equation NT equals gamma over PT relate to the preventive check hypothesis by Malthus? Well, it's actually quite simple. If you assume that agricultural goods are hard to get, they're scarce, then probably on the market they will have a high price. But if the price is high, then in this model we obtain that the fertility is very low, which means that once you have scarce resources, then people naturally tend to limit the number of children that they want to have. You've now reached the end of this video that is supposed to help you to compute the demand for children in the model by Struik and Weisdorf, but that's also a pretext to use a Lagrangian in a utility maximization program. Make sure, as usual, that you've understood all the steps in the computations, and don't hesitate to share your comments and your questions by the usual means.